All right, so we've used three different examples of data so far. We've used string literals, which are stored in the static data area and which are unnamed arrays of chars with a null terminator on the end, so that if you say cout and double less than, that is the insert or put to operator, and the string hello world, that string ends up being displayed on the screen. We've also used parameter variables in order for functions to be passed values for them to use. And we've used local automatic variables inside the body of functions for things like controlling loops and so forth. In Lecture 8 here, we're going to really get into all the different kinds of variables that you can have and various features or attributes of those variables, including their scope, that is which part of the program you can refer to them in, their lifetime, which is from when they're created to when they go away, and their storage class, which specifies where in the system these things reside. Now, the first few slides here repeat the tail end of Lecture 7. In the past, when I've done this material, it's been on different days, so hence the repetition. But we will just dive right into the new stuff. Okay, so here on slide 6, I have a program that has a variable named pi defined outside of any function. Pi is an example of what's called a global variable. And as a global variable, this variable can be accessed from any function anywhere else in the entire program. So I have a function twice here. I'm not using pi within twice. I have a function main below twice in which pi is being used, and so that's accessing the global variable. Let's walk through and see what happens when we run this program. Okay, when I start the program running, as we said in the last lecture, first the code gets loaded into the code segment, and global variables and string literals get loaded into the static data area and initialized if an initialization value has been given. Now, here we have specified an initial value for the global variable pi, and so that value gets stored. Cout and cin and some other things are also in the static data area. Once all of the static data has been loaded and initialized, then the main function gets called, and we start executing the statements in main one by one. In the main function, in the very first statement, we're declaring a variable called 2pi, which is of type double. So storage gets allocated for 2pi in the stack, and 2pi is being initialized with the result coming back from this twice function call. Now, we have to call twice. We're passing the value of pi as an argument down to twice. So that means that within twice, we're going to have a parameter to receive that value. We've chosen to call that parameter x. And x gets created on the stack. All right, so 2pi has been created on the stack, and we're attempting to initialize 2pi. In order to initialize 2pi, we have to call twice first. So twice has its parameter created and initialized, and we're now going to compute 2 times whatever the value of x is and return that. That will then become the value of the 2pi variable back in main. All right, so let's move on to the next step here. When the twice function returns, its parameter variable x is eliminated from memory, and the value that was computed, which is 2 times the value of pi, gets returned back and becomes the initial value of the 2pi variable. So that's the end of the first statement in main. Now, the second statement in main is making use of the cout object. And the first thing that's done with the cout object is to insert or put to the value of the variable 2pi. Okay, so what's going on now? Well, Cout is a global variable. We're making use of that global variable in main. And an argument, namely this value 2pi, gets passed down along with this insert message, if you will, this insert function call. It's a function call in disguise. So that value of 2pi gets passed down and becomes the value of the parameter within that insert function. All right, that value is used and displayed to the screen, and when that is finished, the stack frame for that insert function goes away. Then we have another insert function call. Okay, when that first insert function call is done, we have another insert function call here, also to cout, and so that passes in the argument new line character, which is displayed to the screen. Okay, when that's done, the third and final statement in the main function is a return of 0 back to the system. When main returns, everything about the program is eliminated from memory. And so the memory is now available for reuse by the next program that we run. All right, so here on slide 10, we are illustrating an exceptionally bad random number generator called non-random. Actually, I want to put that over on my other slide, my other screen, so that I can pull my Ubuntu screen up on the right side, and we'll have a look at this program. All right, so here is my program, typed in my VI editor on the right-hand screen. Let's take a look at what we want this program to do and then see what it actually does. Our desire here for this program is we want to display 1,000 pseudorandom integers. Okay, so we've got ourselves a for loop here that's going to count through 1,000 times. Notice, by the way, that I'm using ++i, now that we know about the increment operator, to increase the value of I by 1 each time through the loop. And each time through the loop, I'm going to call the function myrand1, which is my pseudorandom number function. When myrand1 is called, a seed variable is created on the stack and initialized to the value 1234. Then we use the seed in what's called a linear congruential algorithm to compute a new seed. And our goal here is that we get back a new seed each time we call this function. All right, so let's give this thing a try. I'm going to save this and compile it. And run it. Ah, rats. Well, that's pretty non-random. I got the very same value 1,000 times. What's going on here? Well, actually, what's going on here, if you look at it for a second, is fairly obvious. The seed variable here is a local automatic variable. So it is automatically allocated each time the function is called and initialized at that point. Consequently, every time I call this myrand1 function, seed gets initialized to 1234, and then I'm always doing the same computation, so I'm always getting this revised value for the seed of 15,057, and so I'm getting back the same value, 15,057, from myrand1 every single time. What I want to have happen is for the initialization of seed to only occur one time, and then for that previous value of seed to be remembered from time to time as I continue calling this function. So here is a new and improved version of the function in which we're declaring a local variable to be static. All right, when we declare a local variable to be static, then that variable is stored in the static data area. It's not stored on the stack. And initialization of the variable only happens one time when that initialization expression is first encountered. In this way, the function is able to maintain a memory from time to time of what happened the previous time it was called. The only change that we're going to make, so let me do that right now. The name of this revised program is going to be more random. And we'll change the function to myran2. Other than that, the only change I'm making is to put the word static in front of the initialization of the seed variable. All right, so when we run the program now, 1,000 times from main, we're going to call myran2, but only the first time when myran2 is called is the seed variable going to be initialized to 1234. The second time myran2 is called, seed still exists because it's in the static data area, and the initialization is not performed ever again. So the very first time myran2 is called, we're going to compute that same value that we had from myran1, namely 15,057. But then in subsequent times, we'll use the previous seed to compute the new seed. And if I've chosen decent parameters here for this so-called linear congruential algorithm, all right, so this kind of algorithm is called a linear congruential algorithm. It's sort of kind of okay, but there are lots of other much better pseudorandom number generation algorithms. But I will at least get back different numbers now each time I call myran2, or at least that's the hope. Let's see whether that's actually the case. Okay, so here's more random, G++. Let's take a look at it just to make sure I didn't mess this up. More random. All right, that looks good. So let's compile this thing. And run it. Now, in Linux, and in fact, this also works on Windows if you are aware, or maybe you haven't tried this, but it will work. You can pipe this result using a vertical bar symbol into the program more, which will paginate the output. And there we go. Okay, so now we did get 15057 as the first returned pseudorandom value, but then we got a sequence of different numbers. And it turns out if you let this thing run 32,768 times, you'll discover that you do get back each of the values in the range from 0 to 32,767 exactly once. So we're not going to make any claims about the distribution of these values, about how normal or non-normal that might be, but at least we are getting back each of the values in the range, and we're only getting back each value in the range one time in a cycle of 32,768 tries. All right, so that's better. Okay, we're calling this better, but still not very good because the linear congruential kind of calculation just doesn't have really wonderful properties for producing sophisticated sequences of random numbers. All right, so let's walk through the code and see what's going on in memory while the code is executing. When we run our program, as we said, the first thing that happens is that the code gets loaded into the code segment of memory. Then global variables and other static data get loaded into the static data area. Global variables will be initialized, but local static variables won't be initialized until the first time the initialization expression is encountered. So space for seed is allocated in the static data area, but it's not yet initialized because myran2 hasn't been called yet. All right, in main, we do have a local variable, integer variable I, initialized to 0. And because 0 is less than 1,000, we are going to call myran2. At this point, the very first time we call myran2 is when seed in the static data area does get set to 1234. Okay, so seed is 1234 now. We perform our linear congruential algorithm and we get a new value for the seed, which we know is 15,057, and that value gets returned from the myRan2 function. Now, because the seed variable is in the static data area, it continues to exist even though the myRan2 function has returned. Okay? The seed variable does not go away when the myRan2 function returns. We do get back into the main function, and the main function displays that value 15,057 that came back. All right, that's what's going on in this third part of the diagram. Then, in the change part of the for loop, I is incremented to 1. So I has now been increased to 1. Since 1 is still less than 1,000, we're going to call myRan2 again. And this time, the seed that we start with is 15,057, the value that we got back the previous time. And we're going to compute from that a new seed of 21,142. That value is then returned from that value is returned to main and displayed, and this process repeats. Okay, the seed variable, although it is a local variable within the myRan2 function, is stored in the static data area rather than in the stack, so it persists even if myRan2 isn't currently being executed. And in fact, seed will only be eliminated from memory when the whole program is done and the main function returns. Okay, so now we have seen the difference between a local automatic variable, where the variable is created on the stack when the function is called and automatically eliminated from the stack when the function returns, versus a local static variable, which is created in the static data area as soon as the program starts running, initialized just the first time the function that contains it is called, and then persists throughout the entire remaining execution of the program. All right, the next thing we're going to take a look at is the scope of a variable. Basically, the scope of a variable says in which part of the code can I access that variable just by giving the variable's name. Now, for a local automatic variable that's declared within a function body, the scope is from the point where that variable is declared to the bottom of the block in which it's declared. For example, here on slide 19, we have a block of code for this for loop in the function f, and within that block of code is a local automatic variable called I. That variable, the scope of that variable, is just the block, the yellow bounded block that I have indicated within the for loop. That variable I is not going to be visible outside of that block. It is possible to have what are called nested blocks or nested loops that reuse the name of that variable and that create what's called a hole in the scope. We'll see that next when we look at the parameter variable scope. Okay, so for a parameter variable, such as the variable I for the f function, the scope of that variable is the entire block of the function. Okay, so from the opening curly brace of f to the closing curly brace of f, except within a nested block or loop, which is exactly the case that we have here for the for loop. This for loop has its own local variable called I, which hides the parameter variable I inside of that purple region of code. All right, so this parameter's scope is the entire body of the function, except for any hole in the scope that's created by having a nested block. Now, global variables can potentially be accessed anywhere in the entire program except when a nested block is created. So here, for example, I have a global variable called I. This I can potentially be seen throughout the entire program, but I have a local parameter I that's hiding I from within F. I also have, in main, a local variable called I that's hiding the global I from here. So in fact, although I do have this global variable called I, that global variable I is hidden from view in both the F function and the main function. Okay, so let's review all of the variables in slide 19 and their scopes. We have a global variable called I that's visible to any function throughout this entire program, even including functions in other files. But in this particular file, that global I is actually hidden from view because we have a parameter named I in F, and we have a local variable named I in main. So those are holes in the scope of the global variable I. For the F function, as I said, we have a parameter variable named I. Its scope is the entire body of the function, except for this nested block here, where I have a local variable called I, which is only visible within the curly braces for the for loop. Another variable in the function F here is this loop variable J. J is only visible within the body of the for loop. So it's visible, obviously, where it's being declared. It's also visible in the test expression and the change expression, and it's then visible in the body of the for loop as well. And then finally, down in main, we have a local variable named I. This happens to be a local static variable, so it's in the static data area rather than on the stack, but it's only visible within the body of main from the point where it's declared down to the closing curly brace of main. Okay. The lifetime of an object is the duration of existence of the object from when the object is created until the object is destroyed. And basically there are two different lifetimes that a variable could have. If you have a global variable or a local static variable, both of those kinds of things are stored in static data, and so their lifetime is from the moment that the program starts running until the moment that the program is done running. Parameter variables and local automatic variables, on the other hand, are created when their functions or their blocks are entered and are eliminated when we return from or exit from that block or that function. So parameters and local automatic variables have very short lifetimes. Global variables and static variables have much longer lifetimes. The final attribute of variables that it's important to know about is what's called the storage class. And this simply indicates which region of memory the variable is stored in. Global variables and local static variables have static storage class and are stored in the static data area. Parameters and local automatic variables, on the other hand, which are stored in the stack, are referred to as having automatic storage class. Okay, so it's important to understand all of these characteristics, and that's why I've got this page 22 all in red. When you look at the declaration of a variable, that tells you an enormous amount of important information about the variable. Obviously, the name of the variable, and obviously the data type of the variable. Now, when you think about the data type tells you what range of possible values could possibly fit within there. So for this variable I, because it's an int, I know that it can contain a range of values on my machine roughly between plus and minus 2 billion. The data type also tells me what the supported operations are. Okay, so for an int, I know that addition to other numbers is supported. I know that subscripting is not supported. I can't subscript on an int. I know that I can put an int value to cout. So the put to or insert operator to cout is supported. I can't put an asterisk in front of I and try to treat I as a pointer though. All right, so I have this raft of available possible operations. Some of them are available to me for an int, and others are not available for an int. I also know, or at least I should know, roughly speaking, how many bytes of memory the object occupies. The location of the declaration and whether the declaration has static in front of it or not will tell me what the initial value of the variable is. Also, what the scope, that is the region of the program where I can access the variable, is. I'll also know how long the variable survives, that is when it's created and when it goes away, and whether it's stored in the static data area or the stack, or later we'll see things that are stored in the heap. Okay, so I will say one last time that it's very important to be able to determine all of these things from looking at the declaration of a variable in your code, and be warned that I will feel free to ask you questions about all of these things on quizzes, for example. All right, so that is Lecture 8.